A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. Alright, we have a heavy hitter today. Daniel sent us a text prompt, and it is a deep dive into one of the most significant pieces of code ever written. Here is what he wrote to us. Let's talk about how Stuxnet worked, focusing on everything known about the actual technical operation of the code's payload. I want to get past the spy novel headlines and really look at the PLC injection logic, the centrifuge sabotage sequences, and how it managed to lie to the operators while the hardware was literally tearing itself apart.
Oh man, Daniel is speaking my language today. Herman Poppleberry here, and I have been waiting for a reason to go through the Symantec dossier again. This isn't just a malware story, Corn, it is a physics story told in assembly language. It's the moment the digital ghost finally got a physical pair of hands to start breaking things.
It really is the OG digital to physical weapon. And before we peel back the layers on this digital onion, a quick shout out to our sponsor. Big thanks to Modal for providing the GPU credits that power this show. Also, fun fact for the tech nerds out there, today's episode is actually being powered by Google Gemini 3 Flash.
It is poetic, isn't it? One AI helping us explain a piece of code that was so complex it basically functioned like a pre-programmed autonomous agent. Stuxnet wasn't just malware in the sense of a virus that steals your credit card. It was a precision-guided munition. If a normal virus is a grenade thrown into a room, Stuxnet was a sniper bullet fired from 3 miles away that only hits a target wearing a specific shade of blue.
Right, and it had to be that precise because it was targeting the Natanz uranium enrichment facility in Iran. This place was air-gapped, buried underground, and protected by some of the most intense physical security on the planet. You couldn't just email a virus to the centrifuges.
Well, not exactly, because I'm not allowed to say that word, but you're on the money. The air gap is the first myth to bust. People think an air gap is a magic shield. Stuxnet proved that an air gap is just a speed bump if you have enough zero-day vulnerabilities and a thumb drive. It used 4 different Windows 0 days just to move around the internal network. But the part Daniel wants us to focus on isn't how it got in, it's what it did once it arrived at the finish line.
Which was the Programmable Logic Controllers, or PLCs. For the folks who don't spend their weekends in a factory, these are basically the brains of industrial machinery. They take sensor data and tell motors how fast to spin. I always think of them as the middleman between the mouse click on a computer and the actual movement of a heavy machine.
That's a good way to put it. And specifically, Stuxnet was looking for Siemens S7300 and S7400 PLCs. But it wasn't looking for just any Siemens controller. This is where the fingerprint check comes in, and it is honestly terrifyingly specific. When Stuxnet landed on a computer running the Siemens Step 7 engineering software, it didn't just start breaking things. It sat quietly and performed a hardware census. It looked for a very specific configuration of 417 frequency converters manufactured by 2 specific companies, Ferraro Paya in Iran and Vaken in Finland.
Wait, so if it found 416 converters, or if they were made by a different brand, it just stayed dormant?
It did nothing. It was a silent infection unless the environment matched the target profile perfectly. This is why it took so long to discover. It infected thousands of computers worldwide. I think over 60% of the infections were in Iran, but it spread to India, Indonesia, even the US. But on 99% of those machines, the payload never triggered. It was looking for the specific electrical signature of the Natanz centrifuge cascades. If you weren't running a specific array of high-frequency drives connected to a specific model of Siemens CPU, Stuxnet was basically a ghost. It wouldn't even reveal its presence.
That is some serious restraint for a piece of code. Most malware is like a toddler with a permanent marker. It wants to draw on every wall it sees. Stuxnet was more like a professional assassin waiting in the closet for one specific person. So, let's say it finds the match. It confirms it's at Natanz. How does it actually cross the bridge from the Windows PC to the PLC hardware? Because these are two totally different languages, right?
Right. You have Windows running on x86 architecture, and then you have the PLC running its own proprietary logic. This is the man-in-the-middle attack on the library files, and it's brilliant in a dark way. On a Windows machine, the Steve 7 software uses a library file called s7bxdx.dll to communicate with the PLCs. Stuxnet replaced that legitimate file with its own malicious version. So, when an Iranian nuclear engineer opened their console to check the code running on the centrifuges, the malicious library would intercept the read request. It would look at the PLC, see the malicious Stuxnet code, and then quickly Photoshop it out, showing the engineer a perfectly clean, legitimate block of code instead.
So the engineer is looking at the screen thinking, everything looks great, the logic is sound, while the actual hardware is running a totally different set of instructions. That's like a pilot looking at their instruments saying they're at 30,000 feet while the plane is actually scraping the treetops.
Precisely. Well, not precisely, it was a total deception. The PLC rootkit gave the attackers complete control over the physical reality of the plant while maintaining a digital hallucination for the operators. It's the digital equivalent of that scene in heist movies where they loop the security camera footage so the guards see an empty hallway while the vault is being emptied. But it's even more sophisticated because Stuxnet wasn't just looping a video, it was actively rewriting the responses from the hardware in real time to match what the software expected to see.
Okay, so the hallucination is set up. The engineer is happy. Now, what is the actual sabotage part? How do you break a centrifuge with code? I mean, these things are made of high-grade carbon fiber and steel. They aren't exactly fragile.
You play with the physics of resonance. These centrifuges are spinning uranium hexafluoride gas at incredible speeds to separate isotopes. They usually run at a steady frequency of 1064 Hz. Stuxnet had two main attack sequences, which researchers call Sequence A and Sequence B. And the timing here is key. It didn't just attack once, it lingered.
I'm assuming these weren't just turn it off commands. If the machines just stopped, the alarms would go off instantly.
No, turning it off is too obvious. Sequence A was the overspeed attack. It would wait for a period of normal operation, then suddenly crank the frequency up from 1064 Hz to 1410 Hz. It would hold it there for 15 minutes. Now, think about the mechanical stress on a carbon fiber rotor spinning that fast. You are pushing it way beyond its structural design limits. It's like redlining a car engine for 15 minutes straight, while the dashboard says you're doing 50 miles per hour.
But why 15 minutes? Why not just keep going until it explodes?
Because they wanted to weaken the material without necessarily causing a catastrophic plant-wide shutdown immediately. They wanted to create mysterious failures over time. After 15 minutes, it would return the speed to normal. Then it would wait for weeks. It wanted to be subtle. It wanted the Iranian engineers to think they just had a bad batch of rotors or a mysterious mechanical fluke. But then came Sequence B, which was arguably more clever and much more destructive. It would drop the frequency all the way down to 2 Hz for 50 minutes.
2 Hz? That's barely moving. Why slow it down? If you're trying to enrich uranium, slowing down seems counterproductive, but not necessarily destructive.
Oh, it's incredibly destructive because of critical speeds. Every rotating object has a resonant frequency where it vibrates most intensely. Think of a washing machine on the spin cycle. There's that one moment where it wobbles like crazy before it gets up to full speed. That's the critical speed. When a centrifuge starts up or slows down, it has to pass through these critical zones quickly so the vibrations don't build up. By holding the centrifuges at 2 Hz for nearly an hour, Stuxnet was essentially forcing them to sit in that danger zone. The vibrations would become so violent that the rotors would actually touch the outer casing and shatter. It was turning the machines into their own wrecking balls.
That is devious. It's using the machine's own physical properties against itself. And while this is happening, while the rotors are screaming and vibrating into pieces, the guy in the control room is looking at a screen that says 1064 Hz, all systems nominal.
That is the signal masking part of the payload. Stuxnet would record 21 seconds of legitimate normal sensor data from the centrifuges before the attack started. Then, during the attack, it would play that 21-second loop back to the SCADA system. It's the ultimate gaslighting. The centrifuge is literally exploding in the next room, and the computer screen is showing a calm, steady line of perfectly normal operation. It even faked the state of the valves and the pressure sensors. If a valve was supposed to be open, Stuxnet made sure the screen showed it as open, even if the malware had actually slammed it shut to build up pressure.
It really highlights the vulnerability of our trust in digital systems. If the sensor says it's fine, we believe it's fine, even if our ears are telling us something is wrong. But eventually, the Iranians had to notice, right? You can't hide 1,000 broken centrifuges forever. Even if the screen says all good, the pile of scrap metal in the corner tells a different story.
They noticed the failures, but they couldn't figure out why. There's a famous story of the International Atomic Energy Agency inspectors visiting Natanz and noticing that the Iranians were hauling out huge numbers of broken centrifuges. The Iranian technicians looked baffled. They were replacing parts, checking the power supply, looking for physical sabotage, but they weren't looking at the code because the code told them it was doing its job. They actually fired some of their own technicians because they thought they were being incompetent or negligent. Imagine being the guy who gets fired for breaking a machine when the computer says you did everything perfectly.
That's a whole different level of psychological warfare. It's interesting that the code had a kill date, too. Daniel mentioned June 24th, 2012. Why have an expiration date on a weapon?
Yeah, that's a very state actor move. It shows that this wasn't an uncontrolled wildfire, it was a mission with a timeline. After that date, the worm would stop spreading. It also had an infection flag in the PLC memory, the hex value 0xDEADF007.
Dead foot or dead fool?
Most people read it as dead foot. In aviation, dead foot, dead engine is a memory aid for pilots when an engine fails. If Stuxnet scanned a PLC and saw that marker, it knew the device was already infected and would move on. This prevented double infecting a system, which might cause a crash or a memory overflow that would tip off the admins. It was incredibly polite malware. It didn't want to crash the system, it wanted the system to keep running perfectly, while it quietly destroyed the hardware.
Polite, yet it caused 1,000 centrifuges to fail. That's about 10% of their enrichment capacity at the time. It didn't stop the program, but it threw a massive wrench in the gears. Now, Herman, you mentioned that this likely took 2 different teams, one for the Windows side and one for the industrial side. Is that common in the world of malware?
Not at all. Usually, a malware author is a specialist in one area, but Stuxnet required a full stack of destruction. You needed world-class Windows exploit developers to find those 4 days. Then you needed experts in Siemens industrial software. But most importantly, the expertise required to write those PLC function blocks, specifically the modifications to the OB35 and FC1874 blocks, is incredibly rare. You need someone who understands the STEEP7 proprietary language, but you also need a nuclear physicist who understands the exact resonant frequencies of a specific model of centrifuge. You can't just Google how to blow up a centrifuge with a PLC. You need to have the hardware in a lab somewhere to test your code.
Which points toward a nation state. This isn't a couple of hackers in a basement. You need a testing facility that mimics Natanz. You basically need a mock-up of the target to make sure the code doesn't just crash the PLC, but actually achieves the physics-based destruction you're looking for.
There are rumors that the Dimona facility in the Negev desert had a replica of the Natanz cascade specifically for testing Stuxnet. You have to verify that when you send the 2 Hz command, the rotor actually hits the wall. You can't beta test that in the cloud. And that is the enduring legacy of Stuxnet. It proved that cyber isn't just about data anymore, it is about kinetic force. If you can control the PLC, you can open a dam, you can overpressurize a gas pipeline, or you can tilt a power grid into a blackout. We've seen echoes of this in attacks on the Ukrainian power grid and even some water treatment facilities recently.
It's essentially the blueprint for modern industrial warfare. And honestly, the air gap thing still bothers me. We keep hearing that critical infrastructure is safe because it's not on the internet. But Stuxnet didn't need the internet. It needed a human with a USB drive. How did it even ensure it would get onto the right drive?
It used a shotgun approach for the initial infection. It would infect any USB drive it touched, hoping that one of those drives would eventually be carried into the air-gapped facility. It used a vulnerability in how Windows handles shortcut icons. Link files to execute code as soon as the drive was plugged in and the folder was viewed. The user didn't even have to click on anything. Once it was inside the facility, it used the print spooler vulnerability, another 0-day to spread from one computer to another over the local network. It was like a biological virus jumping from person to person until it found the one person with the specific genetic makeup it was looking for.
That's terrifying. It's like a digital version of the bounty hunter that follows you home. So, if we look at the practical takeaways part of this, because we always try to give the listeners something to chew on, what has changed in industrial security since 2010? Are we still just as vulnerable to this kind of PLC injection?
We are better, but the threat has evolved. One of the big changes is the push for code signing in industrial environments. Nowadays, a PLC should, ideally, only run code that has been digitally signed by an authorized engineer. If Stuxnet tried to swap out a library today on a modern, properly configured system, the hardware would see that the cryptographic signature doesn't match and it would refuse to run. But ideally is the doing a lot of heavy lifting in that sentence.
But how many properly configured systems are out there? I feel like there's a lot of legacy gear in power plants and water systems that's 20 years old. Do those old Siemens boxes even have the processing power to check a digital signature?
Most of them don't. That is the nightmare scenario. There are thousands of PLCs out there that don't support modern security features. They were built in an era when security meant a locked gate and a guard dog. For those systems, the takeaway is network segmentation and behavioral monitoring. You have to watch the network traffic between the IT side and the operational technology, or OT side. If you see a computer suddenly trying to rewrite a PLC's function blocks at 3 in the morning, that should trigger an alarm immediately. You need deep packet inspection that understands the industrial protocols, so it can say, hey, why is this engineering workstation sending a frequency change command to the turbine?
It's like having a digital bodyguard who doesn't just watch the door, but watches the people inside to see if they start acting weird. But what about the lying aspect? If the PLC is compromised, can you ever trust the data it sends back?
That's the Byzantine general's problem of industrial control. If you can't trust the messenger, how do you know the state of the system? And for the engineers listening, checking your firmware versions and actually auditing the code on your PLCs against what is supposed to be there is crucial. Stuxnet's greatest trick was making the engineers see what they expected to see. You have to find ways to verify the ground truth of the hardware that don't rely on the potentially compromised software.
Like maybe a physical tachometer on the centrifuge that isn't connected to the network. Something that gives a direct, analog reading?
Analog backups. It sounds old school, but an analog gauge that physically moves a needle based on pressure or speed is almost impossible to hack from a remote computer. If the computer says all good, but the physical needle is in the red, you trust the needle. We've moved so far toward software-defined everything that we've forgotten that physical reality is the ultimate arbiter. If you're running a critical process, you need an out-of-band way to verify that the machines are doing what the screen says they are.
I love that. The high-tech solution to the high-tech problem is a piece of metal on a spring. It's a great reminder that complexity is often the enemy of security.
Sometimes the old ways are the best, but overall, Stuxnet was a wake-up call that the world didn't really want to hear. It showed that our entire physical reality is increasingly mediated by layers of code that most of us don't understand and can't see. When that code is subverted, the physical world breaks. It's not just about losing data anymore, it's about losing the power grid, the water supply, or the factory floor.
It's a lot to think about. Daniel, thanks for the prompt. This was a fascinating forensic look at a digital crime scene. It's wild to think that this all happened over 15 years ago and we're still unraveling the implications. It really set the stage for everything we see in the news today regarding state-sponsored hacking and infrastructure vulnerability.
It's a masterpiece of engineering, regardless of the politics. The sheer level of coordination required to pull that off is staggering. It makes you wonder what's sitting on our networks right now, just waiting for its fingerprint to be matched. Is there a Stuxnet for power grids, or a Stuxnet for hospital scanners, just waiting for a specific date or a specific configuration to trigger?
On that cheery note, I think we'll wrap it up. If you want to dive deeper into the history of cyber warfare, we did an episode a while back, episode 9068, on breaking the air gap, which covers some of the broader context of industrial attacks. We go into some of the more recent stuff like Industroyer and Triton there.
And if you're into the physics of destruction, episode 694 on the GBU-57 Bunker Buster is a great companion to this, looking at the physical side of attacking fortified targets. It's the brute force version of what Stuxnet did with a few kilobytes of code.
Thanks for listening to My Weird Prompts. Thanks to our producer, Hilbert Flumingtop, for keeping the gears turning and ensuring our own PLCs don't start vibrating through the floor.
And thanks again to Modal for the GPU credits. We literally couldn't do this without them. They provide the horsepower that lets us sift through these technical dossiers.
If you like the show, leave us a review on Apple Podcasts or Spotify. It really helps people find us in the sea of content out there. You can find all our episodes and the RSS feed at myweirdprompts.com.
We'll be back next time with whatever weirdness Daniel or the rest of you send our way. Keep those prompts coming. The more technical, the better.
Stay curious and maybe keep an eye on your USB drives. If you find one in a parking lot, maybe just leave it there.
See ya.
Bye. This episode was produced using Google Gemini 3 Flash. Text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts, that's the close from sloth.